Alright, so in 5.1 we're starting to talk about properties of exponents. A lot of this might look familiar from Algebra 1. I remember you all kind of mentioned that you've seen this before, maybe in some context, which is great, so hopefully this should all be familiar to you. Before we talk about these properties of exponents though, there's a key distinction I need to make, just a couple terms that I'm going to use kind of throughout this video lecture, and that's the difference between a base and an exponent. So my base is the number or the variable or the quantity that I'm raising to a power, right? And that power is also called an exponent. Okay, so bases can be numbers, bases can be variables. In this case, up here in the corner, we're considering it to be a variable, but you're going to see in a minute that I could have numbers as bases as well. So my product of powers, right, if I've got two bases that I'm multiplying together, and they've both been raised to an exponent. And what's important here is you can kind of see it, that their bases are the same. In this case, all I'm going to do is I'm going to add the powers together. So the product of powers, all I need to do is add the powers together, add the exponents together. Right, and so my algebraic example, actually let me switch colors here, would be maybe to say if I have x squared times x cubed, well I'm just going to add those powers together. Excuse me. 2 plus 3 is 5, so x to the 5th. And my numerical example would be kind of along the same lines. If I did 2 squared times 2 cubed, well, I could, if I wanted to, I could look at this as just 4 times 8 and get 32. Or I could look at this as 2 to the 5th, right? I'm going to add my powers, and I'm going to get 32. One way I remember this is that multiplication, right? Product multiplication. Remember that multiplication is just repeated addition. So there's that link between multiplying and adding. And that's going to help me really keep some of these organized, keep some of these straight. For a quotient of powers, it's the same type of principle, right? I've got some kind of division. You see again that my bases are the same. And they have to be the same for me to actually combine these. And when I see a quotient of powers, I'm just going to subtract the quotients. Sorry, subtract the powers. So my algebraic example might be to say x to the 5th divided by x cubed is, well, I'm going to subtract, right? 5 minus 3 is 2. And if I want to do this with numbers as well, maybe I could do 3 to the 5th over 3 cubed. And maybe I don't know offhand what 3 to the 5th is. So instead of trying to calculate that, I can just subtract my powers. 5 minus 3 is 2, and I know that 3 squared is 9. So just like we said with the product and addition, we can apply this to the quotient as well. Let me just kind of divide it here. Right, division, just like multiplication is repeated addition, division is just repeated subtraction. And there's kind of our link, and that's kind of the way I remember that link between the quotient and subtraction. So if I have a power to a product, so we talked about a product of a power, now we're going to kind of reverse it, right? I have a power of a product, so I have some kind of a product that I'm raising to a power, and all I'm going to do is, well, it kind of looks like we're distributing, right? It's kind of almost distribution, right? I'm making sure that the powers being applied to both terms in the product. Wrong color. So my algebraic example might be to say x times y to the 5th is just x to the 5th times y to the 5th. And we really wouldn't do this with a number, right? If I gave you something like 4 squared, you wouldn't really ever write it as like 2 times 2 squared, but you could. The more helpful bit, I think, is to say something like 2x squared. This is something that we're going to see really often. And same thing, just distribute our power. So 2 squared times x squared, and we know that 2 squared is 4. So we get 4x squared. The power of a quotient is going to work exactly the same way. So it's still some kind of distribution. I can distribute over my division. So x divided by y to the a is just going to be x to the a divided by y to the a. So if I have something like x divided by y cubed, right, it would be x cubed divided by y cubed. And for a number, this is actually the time where you would actually see the power of a quotient rule being used with a number. So if I had something like 1/2 cubed, right, we'd say it's 1 cubed divided by 2 cubed, and that's just 1/8. Notice that, so this works for multiplication and division. This never works for addition or subtraction, right? I can't do like x plus y squared and get x squared plus y squared. That's not how this works. I go crazy every time I see this on a paper or a test or a quiz. This distribution rule only works for multiplication and division. So all right, never for addition or subtraction, only for multiplication or division. So my power to a power, so now we have something like x to the a, and then I'm also taking that and raising it to the b, and all we're going to do is multiply our powers together. So if I have x squared, let me get the right color here. If I have x squared cubed, well, 2 times 3 is 6, so this is x to the 6th. Same idea here if I did like 2 squared cubed, and again, you really wouldn't see this in this case, right? Most normal people would just call this 4 cubed and call it 64. But for the sake of practicing it, we're going to show it as 2 to the 6th. I'm going to multiply my powers together, which is also 64. So not something we would actually do very often with a number, but it's good practice, I think, just to see it that way anyway. So with negative exponents, so if I have something like x to the negative a, well, what do I do with that, right? I can't express this as being multiplied a certain number of times. Well, what we're going to do is just write it as what we call a reciprocal, right? So I'm going to take it, and you kind of see that it, instead of being in kind of almost like a denominator, or sorry, a numerator, we've moved it into the denominator of a fraction, right? So we actually kind of call this a reciprocal. And that's how I'm going to kind of write it too. So we're going to move the base and the exponent to the other side of the fraction, or the other half of our fraction. So it flips position. And there's kind of an explanation for why this works the way it does, but I'm not going to go through it in this video. Maybe I'll do a separate video explaining it later. But for now, all you got to know is that it just goes in the other side of the fraction, right? So if I have something like x to the negative 3, well, I'm going to put that in the denominator, and when I do that, my exponent becomes positive. So I have 1 over x cubed. I need to be careful, right? Because if I have something like 2 over x to the negative 3, the only thing that this negative 3 is attached to is the x. So the only thing that's going to move into the denominator is the x, not the 2, right? The 2 is not being raised to the negative 3, it's just 2. So of course, if I saw something like 2 to the negative 2, well, that's going to be 1 over 2 squared, and that's just 1/4. These last two don't really need any big explanation. So we're just going to see it as like a definition. We're not going to really do an example of it. But this works every time. So anything to the 0 power is 1. And then anything to the 1 is always itself. So anything to the 0 power is 1, and that sounds a little bit counterintuitive at first, right? You might be inclined to think that, oh, well, if it's raised to the 0, then it's being multiplied 0 times, so it's 0, right? No, never, no. X to the 0 is 1. Anything I raise to the 0 power is 1. And then anything to the 1 power, the first power, is itself, right? Because I'm multiplying it 1 time, so it's just the thing. All right, so here are kind of all of my powers, right? Product, add, quotient, subtract. If I have a power that I'm raising, or sorry, product or a quotient that I'm raising to a power, I can just distribute. If I have a power to a power, I'm going to multiply. And then, of course, my negative exponents get flipped. 0 power is 1. First power is the identity, so it's just itself. So some examples. If you want to try any of these, you can pause the video now and work on them. But I'm just going to go ahead and go right through them. So take the time now to pause if you'd like, and then we'll get started too. So some examples. If I'm looking at number 1 here, I have a squared b to the 4th times a to the 4th b. So the way I'm going to think about a lot of this is to kind of group together my like bases, my similar bases. Right, so in this case, my a's are in common, and my b's are in common. So if I look at this, I'm going to say, well, I'm multiplying everything together, right? Everything here is multiplication. So I'm going to add everything. So this is going to be 2 plus 4, right? And then b to the 4 plus, if there's nothing written here, we're going to assume it's a 1. So this is 4 plus 1. So just to simplify this, I get a to the 6th, b to the 5th. And the same principle is going to apply in number 2. But before we do any of that, we have to take care of this power here. And we had said that my product of a power, or to a power, excuse me, means I'm pretty much just going to distribute this. So what this is going to look like is a squared times b to the 4th squared, and then the a cubed is still going to get carried down. So to simplify that, right, I have my power to a power here, so 4 times 2 is 8, a cubed. And now we have a problem that looks just like the last one we did. So group your like bases, my a's go together, my b's go together, my solitary b goes together with itself. So multiplication means adding powers, so to the 2 plus 3, b to the 8th, and then I have a to the 5th, b to the 8th. So those are kind of my multiplication examples. For division, right, same idea. We're going to subtract, and but we're going to group our like bases. So my x's will go together, my y's will go together, and my z's will go together if I had more of them. With the subtraction, I like to work this out on the side because I think it's really easy to get mixed up in figuring out what kind of needs to go where. So with my x's, I'm going to say we're always going to subtract top from bottom, right? So 1 minus 3. Let me make that a little bigger. So we're going to say 1 minus 3. Well, 1 minus 3 is negative 2. Right, and this negative exponent here is going to tell me that eventually it's going to wind up in the denominator of my fraction. Right? So if I were to start piecing together my final answer, that x to the negative 2 tells me that I'm going to wind up in the denominator of my fraction, and the negative is going to become positive. Same idea with the y's. We're going to subtract. 2 minus 1 is just 1. Anything to the first power is itself. Oops. So, and the positive exponent tells me that it's going to stay up in the numerator. Nothing's happening with the z's, so the z's are just going to carry over exactly where they belong. And you can kind of see that I've simplified everything already. So we're done. In number 4, it's the same type of idea, except I also now have to account for just my coefficients, just my numbers here. So we'll come back to that in a minute. Let's just identify our like powers, or like bases here. Whoops, different color. So my x's and my y's will be separated, and we're going to take this in pieces. So 2 over 4 is going to reduce to 1/2. So if I were going to start piecing my final answer together, I have 1/2. If I were to look at my x's next, well, division means subtract, so 1 minus 2 is -1. That negative, again, is going to tell me that I need to wind up in the denominator here, next to the first. We'll correct that later. And then same thing with the y's. 1 minus 4 is -3. So I'm going to end up in my denominator with a positive exponent. And then to put this all together, 2xy cubed. If you're wondering where that x disappeared to, sorry, that first power disappeared to, switch colors again. Right, where this went, remember that anything to the first power is just itself. Now this last one doesn't look like you can do much with it, except we've got this 0 power hanging out outside. So this problem just got real easy. I don't have to do any calculation because anything to the 0 power is 1.